Okay, thanks Aseem, and thanks to all the organizers for inviting me. So I'll switch gears a little bit and move from field level to actually discussing a statistic, which tries to capture as much information from the field as possible. So this is work done in collaboration with Tom Abel and a bunch of other collaborators. And I'll try to walk you through the statistics and why we think that this is exciting. So structure formation holds the promise to help us answer many important questions in cosmology. Dark energy, dark matter, inflation, massive neutrinos, galaxy formation physics, substructures, etc. But to do all of this, one of the main questions we have to ask is, how do we statistically characterize the spatial distribution of points? These are, for example, galaxies in your survey. And this gives rise to the concept of summary statistics. So what happens is, as you change your cosmological parameters of interest, this will change the clustering of the data, and the summary statistic will respond in response to that. The more powerful summary statistics will capture more information about the underlying distribution. Okay? And so what we really want to make full use of all the cosmological data that's coming towards us is our fast, robust, and interpretable summary statistics. Now, I know there'll be some questions about interpretable, but I'll tell you why I think this is useful. Okay, so most of the progress in cosmology has been driven through two-point correlation functions. Okay, so the two-point correlation function, or its Fourier transform, the power spectrum, is the complete summary statistic for a Gaussian random field. So if you're looking at something like the CMB, you should be using the two-point correlation function. But it does not capture all the information when the density field becomes non-Gaussian. So if you're thinking about late times, and especially on small scales, the field is extremely non-Gaussian. And then the two-point correlation function no longer captures all the information. So, given all the data that's coming towards us, it's time for us to think about statistics beyond the two-point correlation functions. Of course, this is not new. People have thought about this for a while. People have looked at higher order endpoint correlation functions, the bispectrum, trispectrum, etc. Those statistics are robust, they are interpretable, but they are typically pretty computationally expensive to compute. Okay? So today I'll talk about a completely different set of summary statistics and why we think they can be potentially useful for cosmological analysis. So these are called the K nearest neighbor distributions, which Tom and I introduced in this paper. Let me walk you through how we actually measure it. So suppose you're interested in describing the clustering of points over a certain volume. You first sample the volume densely with a set of query points. Okay? Your data points, which are these darker dots, live in that space. What we do is we go to every query point. We ask, what is the distance to the first nearest neighbor data point? What is the distance to the second nearest neighbor data point? And so on. So this first, second, etc., I'm labeling by K. So that's what this K nearest neighbor stands for. It can be first nearest neighbor, second nearest neighbor, and so on. You did this for this query point, you did this for a second query point, you go through the list of all query points and do the same operation. Then suppose you pick just the first nearest neighbor distances from all the query points. You can sort them. And that allows you a quick way to ask what fraction of these query points have a nearest neighbor data point within the distance R. So that's the cumulative distribution function of these distances. You can do that for the first nearest neighbor, second nearest neighbor, third nearest neighbor, etc. Okay, what are the takeaways? The takeaway is that a single measurement procedure, so all of this is a single measurement procedure, is sufficient for a range of scales. This is actually quite computationally inexpensive. This scales as n log n, so quite similar to how the power spectrum would scale. And you get these CDFs. But why are they useful? So you can show that these CDFs, so the CDF for the K nearest neighbor distribution, is equal to the volume average probability of finding greater than or equal to k data points within distance r from any point you throw down in that space. Okay? You can try to write down the generating function for these distributions, and you can show that the generating function depends on all possible endpoint correlation functions of the data. Then if you look at individual KNN distributions, so if you look at CDF of the first nearest neighbor versus the CDF of the second nearest neighbor, they depend on different combinations of the endpoint functions. So by measuring different k nearest neighbor distributions, you can actually start to disentangle what is coming from the 2-point correlation function versus the 3-point correlation function versus the 4-point correlation function, and so on. Okay. So this is, you can also connect it to the 1-point PDF of your data. They represent integrals over the 1-point PDF with the appropriate Poisson factor. But anyway, so what we did was we took a very simple example where we did a Fisher analysis where we showed the same data to something that computes the KNN and something that computes the 2-point correlation function, exactly the same data. Did a Fisher analysis with respect to these cosmological parameters. And we found that in every case, the k nearest neighbor analysis gives you much stronger constraints on your cosmological parameters. But this is a toy model because what we showed these summaries were actually particles from a simulation. These are not halos. So this is just to give us a feeling of how much gain we can expect if we use these k nearest neighbor distributions. What we also found, and I'll come back to this slightly later in the talk, is you actually gain when you combine different nearest neighbor distributions. So this is your constraints on sigma 8. I shouldn't call them constraints. These are your Fisher error bars. So on sigma 8, it improves when you combine the first nearest neighbor distribution with the second nearest neighbor distribution. You keep gaining for a while, but after a point, there is no longer information left for you to exploit. Now, what I showed you was a way to capture autocorrelations in the data. But in cosmology, cross correlations are becoming more and more important. So in this paper, we showed a way of computing cross correlations between discrete data sets using these nearest neighbor distributions. So again, what we do is we sample, or rather we throw down query points on the volume that we're interested in. And now we have two sets of data represented by the blue points and the green points. We go to every query point, look for the distance to the nearest blue point and the distance to the nearest green point. We pick the larger of the two, okay? Repeat that for every other query point. Every query point we go to, we pick the larger of the two distances. And we plot what is called the CDF of, or the joint CDF of these nearest neighbor measurements. Okay? Again, you can show that this joint CDF is the probability of, or the volume average probability of finding greater than K1 particles from set 1 and K2 particles from set 2 within a radius r. You can write down the generating function for these probabilities. What happens now is you see that it depends on all possible endpoint correlation functions of data set 1 and data set 2. So this, if one was red galaxies and the other one was blue galaxies, terms that would appear in the generating functions are red, red, blue, 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 red, and all possible combinations that you can think of. Okay. It's also quite easy to actually isolate the parts of these which come only from the cross correlations and not from the autocorrelations. That's because when you have two completely uncorrelated data sets, the joint probability just factorizes into the individual probabilities. Okay, so you can write down a measure of what the actual cross correlation is by subtracting what would happen when the two data sets are completely, or rather statistically independent. Now, one of the advantages of using this as a cross correlation is this is sensitive not just to the traditional 2-point cross correlations or the Gaussian part of the cross correlations, but rather tests for the absolute statistical independence of two data sets. Okay, so you could have something correlated at third order, which you wouldn't see in your Gaussian cross correlation. What is the use of this? So we found that, if you're looking for cross correlations of extremely sparse samples, So when you have two samples that are actually cross-correlated, but just from the very low number densities, your 2-point measurements of the cross-correlations are swamped in noise. So what I'm plotting here in purple are two sets of halos with this low number density, which come from the same simulation, so they should be cross-correlated, versus the same number densities of halos measured from the cross-correlation measured from two different simulations where they shouldn't be cross-correlated. So those are the orange lines. You can see that the purple line for the 2-point cross-correlation lies within the spread of the orange line, so within your measurement error. But on the right is the same cross-correlation measured in terms of the nearest neighbor distributions. And here you can see that in the case where there is truly a cross-correlation, it stands out in the data. This is just another way of presenting the same information by looking at the chi-square distributions of the null hypothesis and then actual data, but showing you essentially the same thing. So we have talked about cross-correlations between discrete data sets. Another one that's really useful in cosmology is trying to cross-correlate discrete tracers with an underlying field. Okay, so this is galaxy-galaxy lensing. This is 21 centimeter cross galaxies, anything that you can think of. Okay, and so then we looked at how do we describe these sorts of cross-correlations in the nearest neighbor language. And we showed that all you need to measure is for a given query point, within a distance r, whether you have greater than k nearest or k data points within that distance r, and also whether it crosses a certain threshold in the underlying smooth field. Okay, so again, this captures the joint distribution between the smooth field and the number of tracers. And this has, again, the nice properties that it is not only sensitive to the 2-point cross-correlation between the smooth field and the tracers, but all possible combinations of this field and the tracer. So what we did was we went into the simulations and we created a field called delta X here from the underlying matter field such that the cross-correlation or the 2-point cross-correlation between those fields, two fields, are 0. Then we measured the cross-correlation between the halos and this new field delta X. Now, as expected, since the halos are correlated with the underlying matter density field, if you look at the 2-point cross-correlations, once I set this cross-correlation to 0, I also get a 0 in the cross-correlation between the halos and this new field delta X. That's the 2-point cross-correlation. But if you look at how you compute the k nearest neighbor cross correlations, you see a large signal compared to the measurement errors shown in gray. This is again demonstrating that you gain access to higher order cross correlations if you use this method. Okay, so we've talked about autocorrelations, cross correlations between discrete tracers, and field. What are some of the applications of these statistics? I'll walk you through a few that we've already done. So in this project led by Richie Wang, we looked at the clustering of the 1,000 richest red mapper clusters in the SDSS volume. So this is an extremely sparse data set, okay? Just the 1,000 richest clusters. So if you concentrate on the bottom panel, this plots the chi-square distributions of the randoms for these red mapper clusters versus the actual data measurement using the 2-point correlation function. So you can see that there is sort of a detection of clustering using the 2-point correlation function. This is autocorrelation function. But maybe it's something like 3 sigma or something. If you look at the same data, you again plot the chi-square distribution for the randoms, you get a similar chi-square distribution. But if you actually look at the KNN measurements on the 1,000 richest clusters, you get a whopping signal. Okay? And you can prove conclusively that this extra signal actually comes from the non-Gaussian part. You would not see it if you just looked at the Gaussian clustering. So this was this paper by Richie. So this was the first application to data. What we are doing currently is actually our first application to continuous data, where we take the continuum version of these KNN statistics and apply them to the DES mass maps. So what we have here, so this is in preparation and being led by Daya at UChicago. What we have here is including the full DES noise, Fisher analysis comparing the constraining power from just the power spectrum and the second moment, combining the second and third moment. This is analysis that has already been done in DES, and the CDS. And what we find is that in every case, the CD, except for W0, we don't understand exactly why, the CDS do a better job than combining the second and the third moment. This is the actual signal to noise in the data. This is preliminary, so I didn't want to show exactly what we get, but the total signal to noise we get by combining across all bins in DES is higher than the signal to noise we get by any other combination in the data that has been published so far from DES. Okay, so we do have a lot of signal to noise in these k nearest neighbor distributions. I'll talk about how to exploit it in a while. Other things we are looking at are to use these KNN statistics as a test of GR. So the DESI simulation group, I think, released this catalog where they had simulations at GR, different FFR theories, and so on. But they changed the HOD so that they have matched 2-point correlation functions, so monopole, quadrupole, etc. For these same galaxy catalogs, we measured the nearest neighbor distributions, and even though they have the matched 2-point correlation functions, each has a different nearest neighbor distribution. Okay? So this is work in progress led by Jesse Muir. You can also think of constraining primordial non-Gaussianity using this technique. This is being led by Will Coulton. Again, we have initial hints that the nearest neighbor measurements, once you marginalize over the free parameters of your HOD, do a better job of constraining FNL than the power spectrum plus bispectrum. Okay? So all of this has been showing you actually measurements of signal to noise. They never actually go all the way and model the signal. So that is what we need to do next. But how much time do I have? Okay, I'll go over this part a little quickly. So to do a full cosmological analysis, we need a way to model these k nearest neighbor distributions. What we showed in this paper is that if you're looking to exploit information only from the quasi-linear scale, so say you don't want to go below 15 megaparsecs or so, the ingredients that you need to model the k nearest neighbor distributions are the same as the ones that people have already used for modeling the 2-point correlation functions on these scales. So in this paper, we looked at a particular model where you combine a second-order Lagrangian bias model with a full n-body evolution to get the full displacements of the particles. To model the nearest neighbor distributions, this has already been used to look at 2-point correlation functions. We have the same number of free parameters. We get very good fits for the nearest neighbor distributions down to say 15 megaparsec or so for the first nearest neighbor distribution, 20 megaparsec or so for the second nearest neighbor distribution. Just for context, the 2-point correlation function for this method actually matches down to about 10 or 12 megaparsecs. But what this allows you to do is get a sense of how much improvement you can expect on your cosmological parameters after marginalizing over the relevant bias parameters. And so you can see that compared to just the power spectrum analysis that people had done before using this method, we get a factor of 3 improvement on sigma 8. Most of this improvement actually comes from better constraints on the bias parameters. This is actually known. So if you combine power spectrum with bispectrum, you break the bias degeneracies because they depend on the bias in different ways. But since the nearest neighbor distributions have information about all the endpoint correlation functions, you're just better at breaking these degeneracies. Okay? We are trying to see if there's a simpler way of replacing the n-body part of our previous model with just a Zeldovich approximation. So this is very preliminary work with Andrei Obilian and Marko Simonovic. This is in preparation. But if this works out, then you can basically build an emulator as a function of cosmology and bias parameters. Go to full redshift space, do whatever you want, and that'll be really quick. So this is just starting. Hopefully it will turn out. In the last 5 minutes, I will talk about the connection to other statistics. And I'll return to my point about these being interpretable. What that allows you to do is to understand the connections between different statistics that people have proposed. And you can meaningfully test one against the other and see in what context one would do a better job than another. And so we have already worked out the connections between the nearest neighbor distributions and the various endpoint functions, the moments and the cumulants, the 1-point PDF, the counts in cell, and so on. In the last 5 minutes, I'll talk about this connection between the KNN CDFs that I've been talking about and something called the Minkowski functionals, which people have already used in cosmology and actually across various different fields. So again, this crops up in cement mixing and things like that. So I'll describe what the Minkowski functionals are and specifically what the Germ-Grain Minkowski functional is. That's the one that's more relevant for discrete data. So what you have here is an original pattern. So you have some data points lying about here. What you do is you grow spheres of radius r around these centers. Okay. So when you have a small radius compared to the mean interparticle separations, these spheres are completely distinct objects. As you increase the radius, these spheres start intersecting. Okay. Now, when the radius is really large, you basically form one single object, which is connected, one single connected object. Now, what the Minkowski functionals say is that if you characterize the volume, the total surface area, the total mean curvature, and the total Euler characteristic. So Euler characteristic, you can think about it as the number of disjoint objects on this plot. Okay, that's a very crude description, but for this talk, we do. If you characterize these 4 numbers, you have described everything about these surfaces or these, what should I call them, objects. This has been proposed as a way. Yeah, okay. Another thing I should point out is that how these objects merge and form into a single figure depend on what the distribution of these points were. Okay. So by characterizing these Minkowski, the Minkowski functionals on these shapes, you are gaining information about the original pattern of the data. Now, this, of course, has been in use for many years. This is taken from a paper which measured the Minkowski functionals on the SDSS data in 2014. So I just want to show you a very fun connection between the Minkowski functionals and the KNN statistics. Okay. So here again, I've just taken some 100 data points distributed over a certain, this is an area, not a volume, but it will serve to demonstrate what I want to show. If you ask, give me the list of all query points whose distance to the nearest neighbor data point is less than or equal to a certain number, you get all the green points, which correspond exactly to the volume. So this is an area, but think of it as the volume in 3D of the Minkowski functional. Okay. If I ask for where the intersections are, these are actually all the query points whose second nearest neighbor distance is less than the same distance r. So that tells you all the intersections. Now, if I ask, where are all the query points such that the nearest neighbor is between some radius r and r plus epsilon? You get these. These actually tell you about the area of those figures. Okay? You can convince yourself that the derivative of the nearest neighbor CDF is the area that appears in the Minkowski functional. The mean curvature is slightly more difficult to get an intuition about, but once you start on this path, you can easily show that the mean curvature is the second derivative of the first nearest neighbor CDF. The points which start appearing in a non-trivial way for the second derivative are these points where the 2 circles intersect. So in 3D, these will be actually circles where 2 spheres intersect. And these actually lie on the Voronoi tessellations because these are points that are equidistant from the first nearest neighbor and the second nearest neighbor. And then very funnily, if you take the third derivative of the first nearest neighbor CDF, you actually get this discrete jumps at exactly the radius where two of these spheres intersect. So this is how the Euler characteristic changes discretely as the spheres merge into a single object. So what you have basically is that the four Minkowski functionals are nothing but the derivatives of the first nearest neighbor CDF. And so the information in the first nearest neighbor CDF and the Germ-Grain Minkowski functionals are formally the same. You can either know the function as, you can know the CDF as a function of all R, or you can know the function and its derivatives at a point. So the CDFs are actually the generator of the Minkowski functions because its derivatives give you the Minkowski functionals. You can either see this as a quick, the nearest neighbors measurements being a quick way to measure the Minkowski functionals. But on the flip side, the Germ-Grain Minkowski functionals are actually not utilizing the higher order nearest neighbor distributions. And we have shown before that the higher order nearest neighbor distributions have independent information on cosmology. So in that sense, using the nearest neighbors and multiple nearest neighbor distributions can be a way of getting more information about the cosmological parameters than the Minkowski function. Okay, I think I'm out of time, so I'll leave my summary up here. So understanding structure formation can help answer some of the most fundamental questions in physics. To exploit the data that's coming at us, we really need to go beyond 2-point statistics on small scales. I've shown you one possible statistics to get there. So these are the k nearest neighbor distributions. These are cheap and interpretable, shows much greater statistical constraining power in every test case that we have thrown at it. And if you have any other suggestions, I'm very happy to hear it. These can be modeled using ingredients similar to those already known for 2-point correlation functions, so we don't really have to reinvent the wheel. And it has many possible applications in cosmology, galaxy surveys, 21-centimeter cross correlations, gravitational wave clustering, and beyond. With that, I thank you, and I'll take your questions.
Questions? Okay, here in the first row.
Can you hear me?
Yeah.
Yes.
So what scales did you use for your constraints? And so as in the forecasts that you showed where,
This one?
yeah, so for most of those.
Yeah. So if you, I went over this a little quickly, you can see a gray shaded region. So we throw out those scales because we see that we don't get a good fit to the nearest neighbor distributions on those scales. So the scales that were included here were for the P of K analysis. This went down to, in real space, this went down to about 10 megaparsecs. For the KNNs, we started only at 15 for the first nearest neighbor and 20 for the second nearest neighbor. 20 megaparsecs, yeah.
And is that something that we can right now model, or is it like beyond our modeling capacity?
10 megaparsec, if you're, so these papers that originally, proposed this hybrid EFT model, they showed that for the 2-point function, you can indeed model down to 10 megaparsecs. And we are using this to emulate 2-point statistics down to those scales. Yeah.
Nick and then Hector.
I had a couple of comments on this very elegant talk. So I think it was Zeldovich who famously said the trouble with non-Gaussian statistics is like talking about non-elephant animals. There's just so many to choose from, and all worthy of study, no doubt. But just, it seems to me there's something nice about, the standard 2-point, 3-point hierarchy, in that there's a sort of model underlying cosmology that we see these points of light, galaxies and stuff, which are sampling in some way an underlying field, which is called the Poisson sampling model, right? And the beautiful thing about the 2-point, 3-point, 4-point is they don't care how you sample that field. If you choose red galaxies, blue galaxies, or whatever, And it always seems to me that nearly all statistics that focus on points primarily rather than the underlying field are going to have some sort of extra dressing on them that we're not really interested in.
That's a very good point. And in fact, these endpoint functions that I'm talking about, these are endpoint functions of the continuous field. So you can show that the statistics that I spoke about, you can model them as being Poisson sampling of an underlying field. And these nearest neighbor distributions are sensitive to the endpoint correlations of the underlying field. So whenever I have the xi of k's, these are not the endpoint correlations of the data points. These are endpoint correlations of that same underlying field.
Right, but why don't we just talk about those?
Of?
So the nice thing about this, the 3-point function is I can compare two people's different 3-point functions. Someone's looked at spiral galaxies, blah, 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 nearby, someone else looking at extremely red galaxies. But even though they're very different number density, I can directly compare them. The KNN is going to look very different for those two.
That's true. For many of these 1-point measurements, the number density remains in there.
Yeah.
That I agree with. Yeah. But if you want to capture more information from the clustering, see the problem with the 3-point function is that it gets difficult to compute. It takes time. Also, you do not know how much information you're missing by not going to the 4-point distributions. Okay. Here, it's very easy to check if you're getting more information if you go to k+1 at nearest neighbor. It takes the same time. And see if there's any more information to be gained from going there. So, I'm not going to claim that there are no drawbacks to what I'm talking about, but there are pros and cons to every statistics.
The other nice thing, if I could just sort of twist the question a bit more, is the other nice thing about the 3-point stuff is that it relates directly to physics through the BBGKN hierarchy. You've got the cosmic energy equation relating the 1-point velocity statistic and the 2-point matter distribution. You've got the cosmic virial theorem relating the 2-point velocity field to the 3-point galaxy field. These are things you can measure, right? And there's a parameter in there which is really interesting. It's how much matter there is in the universe. Is there anything similar, any sort of physical question to which these are the answer? Or is this, a statistic looking for an application?
I'll have to think about that particular one. I don't know the answer off the top of my head, but we are essentially building the statistics from the same 2-point, 3-point, 4-point. It's just they are weighted differently and they're summed in a particular way. So you see that this is an infinite sum of those same endpoint correlation functions.
Okay, thank you.
Okay, so we're eating into the coffee break. So quick question, Hector, if you want.
Yeah.
Very good.
So what we've done for our analysis is we use the Quixote simulations. So we have 15,000 realizations at the same cosmology. We use those to measure the covariances for all of our analysis. And the point is that going forward, we definitely need a forward model. If we have many simulations, many realizations at the same cosmology, it shouldn't be a problem to characterize the covariance matrix.
Okay, thank you. Let's thank Arka again.